Alright guys, this is our final video, our final lesson of this year. We are in Unit 10 on limits and continuity. We are finishing up continuity, and our topic today is, right at the top in yellow, intermediate value theorem. The formal definition is, obviously it's right here in front of us, but it's pretty straightforward. It says that if I have a continuous function, and I'm just going to look at that function from x1 to x2. So like I pick a and b being two x terms. So let's say here's my a and here's my b. Okay, so -3 and 4. So on the interval a to b, if I know that this graph is continuous as a whole function, then the graph takes on every y value between the y value for a and the y value for b, which is called f of a and f of b. So let's say that if we plugged in, so our xy table looks like this. So we plugged in x is -3 and we got 1, and then we plugged in 4 in for x and we got 4 for y. So we have this point here, -3, 1, and we have 1, 2, 3, 4, 1, 2, 3, 4. We have this point here. So if we know f of a, f of b, and the graph is continuous, all it says is I am guaranteed to at some point cross, like if I wanted to map my function from a to b, I could do that, right? I could do any sorts of things. I could go all squirrely and get up there, right? So it doesn't matter how I get from point A to point B. The intermediate value theorem says that if I know my x and y for A and my x and y for B, then I know that every point between 1 and 4 must be touched as I cross from A to B. So I am going to draw that straight line back. And in other words, somewhere between -3 and 4 in the x, somewhere between here and here, my pencil doesn't leave the paper, but I go from 1 to 4. So every number between there, 2 and 3 mainly in this case, are going to be values of my graph. A function is continuous on the closed interval, then it takes on every value. In other words, that I have to cross 2 at some point, and I have to cross 3 at some point. Do I cross any other numbers outside of that window of 1 to 4? Maybe. We don't know. So my graph could go way down here like this. It could go way up here like this and end at 4. That's totally possible. But in order for this thing to fill in the rules and the requirements of being continuous, I for sure know that I will have to cross 2, 3 in order to get to 4. So, I feel like I've dwelled on that long enough. Oh, here you go. Here's a good one for you on a Monday morning. Why did the chicken cross the road? Well, the answer is the intermediate value theorem, right? See, because if the chicken's on one side of the road, and then the chicken ends on the other side of the road, then according to the intermediate value theorem, if the chicken started at point A and ended at point B, it must have crossed the road. Okay, sorry, that's probably way too dry for you guys. So let's move on. Let's look at some examples. So, AP exam, a lot of good questions, such as this one here. Given a table, x is 0, 5, 7, 9, 14. So I have this. Let's change the blue quick. I have this values. Coordinates are 0 and 3, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There you go. No, but seriously, so we've got like So we're like here, and then 2 more later we're up here, and then we're down here. So just imagine graphing this thing. That's way too messy. I'm sorry. Just use your own head to visualize these points. But these are XY points. So 0, 3, and 0.35, and 5, 4.25, and so on. But as we look at this table, the AP exam question would ask, given the table above, several measurements of the velocity are being shown. Given that the velocity represents a continuous function, what is the smallest possible number of times where you hit exactly 4? It's asking if I were to draw this graph, like plot each coordinate, how many times would I be guaranteed to cross the 4 meter per second mark? So, for example, I don't know, just blue. Okay, so here's one example. We know that at time 0, we are already moving. We are we are somewhere around this coordinate right here. 0 seconds, we are 3.35 meters per second. We also know that at 5 seconds, we are traveling at 4.25 meters per second. So 1, 2, 3, 4.25. So we're somewhere around here. Right? So we're like that. If we were to look at the graph then, so somewhere between 0 and 5 seconds, I'm going to use straight lines because it's easiest, but somewhere between 0 and 5 seconds, if we are continuous, if my pencil does not leave the paper, then it is guaranteed that at some point I was traveling across this line for the 4 meters per second mark. That is probably the straightest line I have ever not drawn. Sorry about that. There you go. Again, this is one of the points that we are guaranteed. This is where V of t is exactly 4 meters per second. So for sure here, we crossed the 4 meter per second mark. Now the same thing's going to happen between 5 and 7. I promise I will not graph each of these, but at the 7 second mark, 2.75. We are somewhere down here, about 2.75 seconds. Again, if my graph is continuous, then from 5 to 7, I cannot lift my pencil, but I have to get from 4.25 to 2.75. In order to do that, I crossed the 4 meters per second mark. So this is another one. I'll put that one in green. That's another one of those that we had to have crossed the 4 meters per second mark. Now, if you look from 7 to 9 seconds, I start at 2 3/4, I end at just over 2.5. There's a possibility that, let me change this to some other crazy color, that from 7 to 8 to 9, so somewhere between here and here, that's not the best color, but yes, I can draw my straight line and say, no, I didn't cross the 4 second. There's a possibility that all of a sudden, for some freak accident, my graph does go crazy up to 4 or 5 meters per second, but it's not guaranteed. So I cannot say that the smallest possible number of times, it's not guaranteed to have crossed it, so I'm not going to identify that. So here, no. From 9 to 14, yes, I had to go from 2.5 to almost 5, somewhere between there with a continuous graph, pencil not being lifted. I'm guaranteed to have crossed that. So from here to here, I did cross 4. So given the velocities, what is the smallest possible number of times? The smallest possible number of times is 3. There you go. Let's do one more. Guaranteed to be at rest. Okay, so this example, no different. It's just a different scenario, but it's asking kind of the same thing. Is there ever a time when the particle is guaranteed to be at rest? Okay, so we still have time in meters per second velocity. But we are trying to figure out, was it ever guaranteed to be at 0 or at rest, 0 meters per second? Well, from 0 to 5, it could have been, but it's not guaranteed because we only can draw our guaranteed line between 3.35 and 4.25, which does not cross 0. 4 1/4 down to a negative velocity of negative 2.56, yes, that one absolutely would. So we're at 1, 2, 3, 4, and so we go, let's say, from here down to negative 2, we had to have crossed 0. So there's one. 7 to 9, not guaranteed, is possible. It's always possible, but not guaranteed because we're negative and negative. 9 to 14, absolutely. From negative 155 to positive 179, we had to have crossed that 0 mark. So is there ever a time guaranteed? Yes. 2 times. You'd want to answer a little bit more in detail than that, but for the video, I just want to keep working. So let's see. I'm actually going to have to stop this video here. We're getting past 10 minutes here. So thanks for hanging on. I will make part 2 here real quick, and we'll be done for the year. So thanks for listening.